Yeah, so it's the 50th anniversary. It was my 50th birthday. There was all this stuff about it was the 50th anniversary of the Flintstones going on TV, so I figured that's as much of a good of a fun fact as anything. So I'm going to give a talk about safety, and there's some sad bits in this. So just like, there's some bits here where actually it gets a bit scary because this is about safety. And I'm just going to tell you the motivation for why I'm worrying a lot about safety now. So if you think about all the people migrating to cloud, the first thing you do in cloud is just go faster. You get something done really quickly that was going to take you months. You do it in minutes or hours or something. So that's fine, some simple thing. The next thing you do is some large scalable application where you want to distribute it around the world, and you have to buy data centers in all these countries. You do this large global scalable, very cloud native applications. You'd spend a lot of time building them to be auto scaling and efficient and all these microservices and stuff. But one of the things that's happening right now is people are looking at their data center coming to end of life and going, I don't want to spend another $100 million on a big data center when I can just open a cloud account. I can open an AWS account and get basically more functionality more easily on day one and not have to do all of this upfront capital investment. So increasingly, a large number of our customers are just doing data center replacement. And the last 2 or 3 years, we've really got into this with some of our customers. But then when you get into that data center, the back end of that data center is the things that run the business. And it might be flying planes around or running industrial machinery or moving trillions of dollars around. And we want to make sure that the patterns we use to do that don't tank the US economy or kill people or all those kinds of things. So we're starting to come up with some patterns for the most critical workloads that, the things that get automated, I really, really want that to work all the time, right? So I'm starting to sort of insert myself into these conversations, and I want to do a talk about a dynamic non-event. So a dynamic non-event is a safe system. Like dynamically, meaning it's got all kinds of things being thrown at it, and it generates non-events, right? So it's not like you're having an incident review, you have a non-incident review. So I'm going to talk a bit about that. So this is from one of the safety professionals. It said, work in complex systems is bounded by 3 constraints: economic, workload, and safety, right? So if you're doing something, right, if you make it, what it's basically saying, it's like, fast, cheap, or safe, pick one. If you want to do it more cheaply, right, you're going to actually make people work harder, or you're going to do it less safely. Or if you want to do it more safely, you either have to spend more time on it or spend more money on it, right? So that's basically the point he's making. Fairly obvious point. But how did we all manage to get here today without having an event? Right? I actually had a minor event yesterday. I was in Denver for GlueCon, and my plane was delayed by, apparently there were some thunderstorms at San Francisco, so I had a couple of hours delay getting here. But it was a non-event because they were able to fly a bit later, right? So I had a near miss of not being able to get out of Denver, right? So that's that kind of thing. And the people that didn't make it here today, we have survivor bias, right? So we're the people that finally got here and we didn't get stuck in traffic or be stuck in the wrong city or something went wrong. So this is where it gets a bit more topical. So here's an event, right? You might recognize. So if you fly Southwest, when you get on the plane on Southwest, you get to pick your own seat. Right, so who is no longer sitting in window seats? And who's trying to figure out how far back in the plane you want to be? Because if you look, that's the window that blew out. It's not the one next to the engine, right? Because you're flying at 400 or 500 miles an hour, the bits go backwards, right? So this is an interesting problem, but the thing that's really, really interesting about this is this was the first fatality in 9 years, since 2009. The one fatality in the entire US aircraft industry. Right? That is one of the safest safety records you could possibly get. And that's what's interesting. So why is flying so incredibly safe? Like, driving to the airport is the scariest thing on your trip. And driving back from the airport and hanging around in you could probably trip over in the terminal, and there's probably more people dying from that. But once you're actually on the plane, you're one of the safest places on Earth, right? Which is a kind of a weird thing. So I want to just highlight something I did recently. I visited the North Pole. I was flying from Dubai to San Francisco on this Emirates flight on an A380. And I realized, well, the first thing you do is you fly over Iran, which is that sounds bad. I don't want to be flying over Iran. And then a whole bunch of countries ending in Stan, or that I didn't like, that I only ever heard of on the news when something bad was happening. And then Siberia. And then we were physically right on the North Pole. And the fun thing about that is that your time zones go from 6 p.m. to 6 a.m. instantly, because it's a 12-hour flip as you cross the North Pole, because all the time zones come together there. And the flight compass was sort of flying around and around. It was really cool. So I've been to the North Pole, but I was quite high up at the time. So there's a camera in the North Pole looking, on the plane looking down, so I took a picture of what it was showing. This is when we were at the North Pole. There's big cracks in the ice in February. There's not supposed to be cracks in the ice in February. It's a whole another subject that I want to worry about. And this is the view out of the window. That's the sun. It's not really sunrise or sunset. It's just sitting there, right? It's just going to be there for the next month. It'll gradually move up, right? It's sliding around the horizon as you go, which is very cool. All right. So that is one of the most inherently dangerous things you could ever do, is try and fly over the North Pole in a tube of metal, like at 50,000, and it's minus 51 Celsius and all these things outside. So it's a pretty scary thing, but they do it. It's routine. So here's a book that I've been reading recently on workplace fatalities. Why am I reading about fatalities? Because a lot of the things that go wrong, when we have a major outage, it's actually not that different to one of these fatalities. It's like there is no company in the world who has a plan for how many workers they're going to kill this day, right? It's supposed to be 0, right? It's one of those, I want 100% availability, is I don't want to kill people. Right. And unless you're building battlefield armament systems where you are supposed to kill people. But if you don't work for the army, then watch out for it. But here is an incredibly interesting thing from the book. Airlines with the fewest incidents have the highest mortality rates. This was measured over a long period of time. This is backwards the way everyone thinks, right? So if you have fewer incidents, you get more fatalities. And the ones that were reporting more incidents were getting fewer fatalities. Right? And this has to settle in, and you start thinking, so why is that? It's because they have a culture of 0 incidents. You suppress the reporting. You get a culture of blame, like we have those little signs you see at the job site, say we've had so many days without any injuries. Somebody's probably going to die there tomorrow, because they're suppressing all of the small things that might be reported that might build up to actually, that machine that you could have fixed, but that would require reporting a small thing is actually going to go completely wrong. So this is a really, really interesting point. And if you think about what we're trying to run reliable systems, right? We're trying to build systems that don't lose trillions of dollars or kill people or put companies and countries out of business. So there's this other book. Anyone read this book? A couple of you? I thought you probably would. So I go around telling people, I've been telling people for years to read this book, but I also tell them don't read it if you're on a plane, because it's got lots of plane crashes in it, and don't read it if you have a friend in hospital, because there's a bunch of things going wrong in hospital in it. And that's so most people have gone, yeah, I'll just put it on my thing. It's like, Schindler's List is one of the top-rated movies on Netflix, and nobody watches it. It's too depressing, but it's a 5-star movie, right? So it's beautifully made. Don't watch it, right? So this is a really interesting book. So I'm just going to walk through chapter 2 of this book, because this is the thing that really stuck with me. It was a really, really interesting way of thinking about things. And chapter 2 is about one of these. It's a DC-9. Or actually, this one was an MD-80 or an MD-80 something. So Alaska Airlines fly these little planes, and you've probably flown on one. It's the one with the wing, the engine. If you're sitting at the back, it's the one with the engines are deafening, right? So January 31st, 2000, there was a plane, Alaska 261, and it was flying from Mexico to Seattle, and the pilots report they're somewhere near LA and say the horizontal stabilizer appears to be jammed. That's the thing at the back that tries to fly the control altitude. So they start diverting to LAX. They disengage the autopilot, and the plane basically nosedives. So then they were pulling like hundreds of pounds of force on the control plane to keep it level. So they reduced speed, put the flaps out. They were at 17,000 feet over the ocean. trying to get the plane into trim to come in and land, do an emergency landing. There was a whole lot of thumps and a really loud noise. Then the nose pitched down at 25 degrees a second. Just, right? This is where it gets a bit scary. So now the plane's pointing straight down. This is not, I'm just going to, spoiler alert, this doesn't end well. Just to kind of take some of this. So then they're upside down. Planes don't fly upside down. This kind of plane doesn't. So they tried to roll it back upright. But when you're upside down, the aerodynamics doesn't work right. The engines both stalled. So you could basically, it just fell out of the sky, hit the ocean, and killed a whole bunch of people. So what went wrong? That's the story. The book is a very much more like detailed, like what they were saying. The pilots had no idea what had gone wrong. This is the thing, though. 2,300 similar planes had done 95 million flight hours, and they'd never had the problem. This problem had never occurred before. Right? So, well, what's your probability of this thing happening measured over, and they built the plane in 1962. It went into production in 1965. It was designed on slide rules in 1962. And they still fly them. The 717 is actually a pretty good plane. And it's, it's not like it happens often. This isn't a frequent occurrence. So how do you deal with something that's that non-eventful and still deal with it? So the question here is what went right? So for 93 million hours, human beings were making the thing work, but they were making non-events out of this potential problem, right? And the way that you do that is by having redundancy in your system, by having safety margins, and by doing inspections and maintenance, right? Those are the compensating controls that basically take care of these things. So the back of this plane, that's this, you can kind of see there's a sliding sort of bit attached to it. There's a big jack screw that cranks it up and down, and as the fuel works in the plane, it trims itself by moving the entire tail plane. So it's not the elevator, it's the entire tail plane, right? So this is kind of how it works. There's a motor, it's even got an alternate, a backup motor, some gearboxes, and this jack screw that is cranking the whole thing over. So you're supposed to maintain it, supposed to inspect it, supposed to lubricate it, but what happened was the screw stripped. So there's like a big nut on this screw thread, screwing it up and down, and this nut stripped, and then the elevator basically starts flapping, and basically the elevator went jammed leading edge up. So now you're trying to fly a plane where the back wing is trying to dive you all the time. So how do we get here? Launched in 1965, they said you're supposed to lubricate this thing every 300, 350 flight hours. It's about every 2 weeks. And there were committees, there were reports, there was analysis. Everyone said, that's a bit too frequently. We can push this to longer intervals. So here's what happened. 1965, every 2 weeks. They kept that going till 1985, and then the air industry deregulated. Now, the interesting thing is, before and after air industry deregulation, the number of incidents of fatalities continued to decrease. So when they deregulated, there wasn't a sudden increase in problems. And in fact, over time, the air travel has got safer and safer and safer. It's one of those continuously getting better things. But anyway, they basically pushed it to 700 flight hours in 1985, and then it pushed it to 1,000, and then it ended up at 1,250. By 1991, they're up to 1,600 flight hours, and then 1996, they said, we'll do it every 8 months, which is about 2,550 flight hours. It's okay. So this is the drift, right? And still, nothing had ever gone wrong. It just seems perfectly safe, nothing's ever gone wrong, right? Parts showed it hadn't been lubricated in about 5,000 hours, right? Okay. So there was a lot of safety margin in this system. And so that was the lubrication. Then there's this inspection check. You're supposed to look at it and see if it's okay. In 1965, they thought this thing would have a 30,000 flight hour design life. A few of the inspections, yeah, it's not quite that good. Let's do some more inspections on it. And then deregulation, it went to 5,000 to every 26 months, 30 months. And 30 months is about 9,550 flight hours. So, okay. Then there's the tolerance. You've got to measure. You're inspecting it. You're looking, is it worn? So then there's this tolerance thing. So the last time they inspected this plane was in 1997. Remember, it crashed in 2000, at the beginning of 2000, right? And the where was right at the limit, and it was just at the limit where you could pass it. It was just, they were kind of, actually somebody said, it's on the boundary, what should we do? And then they retested it a few shifts later and got it to be under the limit. So they did not maintain that, right? So there's a few warnings here. This is how maintenance is done, right? You're standing on a ladder, reaching into a panel at night in the dark, in the rain, whatever, trying to measure this thing, right? Using a tool that wasn't even calibrated right from the manufacturer. So you can just see these things building up, right? So this is the real thing we can learn from this. Like, it's a reporting and learning culture. Humans use intuition judgment to see things, fix things, and report things that might be wrong. If you have a zero tolerance for any kind of incident culture, you're making people not report things that won't go up. There was actually somebody tried to report this back in '97 that they thought this was dodgy, and they got overruled eventually, and the plane took off, and everything was fine. And 3 years later, the plane's still flying, right? So were they right or were they wrong, right? It should have gone through another test. It should have done better, right? So these humans are causing these non-events. As you start automating systems, you can automate some of it, but sometimes you still need a human in the loop to make sure there's a non-event, or you have to think about how is your automated system maintaining these margins. And here's another example. This is from a slide deck I do on chaos engineering that you can find on my GitHub site. I'll put the URL up later. So a fire drill, right? It's pretty boring. Everyone goes and stands in the parking lot and does a roll call. Everyone has done this. Everywhere in the world I go, if I show this slide, everyone knows this, right? Every tall building in the world has a "don't use the elevators in event of fire" sticker. It's one of the most universal things. But one day, there will actually be a fire, and you will get out alive because people aren't standing in line for the elevator, right? So that's a really interesting sort of way of thinking about it, because now you think, who's running the fire drill for IT, for the systems you run, right? And this whole idea of chaos engineering basically pops up at this point. It's like somebody somewhere should be running the game days and the practice sessions and trying to figure out how much margin do we actually still have? And you get the economic pressure to speed things up a bit or spend a little bit less time on something, and how much safety margin are you actually burning? And can you figure out how much margin you actually have left by running a little game day or a chaos experiment to say, yep, we've got this much buffer, and we don't want, I've got this defense in depth for my availability, and if I knock this one out, I've still got 2 more, but the probability of getting all of them going out is still an issue, so we want to back off a little bit. So you can start making a case for why your safety needs to be better or your availability, not spending that, reducing the time to do something or cutting the investment in safety. So this is this definition of safety. Safety is a dynamic non-event. And to make systems safe, you've got to instrument and study the non-events, and you've also got to provoke non-events, which is the chaos engineering, the game day, the failure injection. So you're trying to inject something which you expect to be a non-event. And if it turns out to be an event, you turn it off really quickly and go, sorry guys, it was supposed to survive that poke, right? But in particular, look for near misses and outliers. And why is the airline industry so safe? They have a program where every near miss, anything that ever goes wrong on a flight is reported and gathered and analyzed. They don't only analyze the failures, right? They're not waiting for the next Southwest plane to have an engine blow. They're instrumenting every single tiny thing that ever goes wrong on a plane. And because it's such an inherently dangerous thing to be stuck in a metal tube flying through the air, there is a culture of making it safe that has really achieved. So I think there's things to learn from the airline industry. So you got to beware of drift, economic workload pressure into this unsafe territory. So this is actually a slide. I moved it from PowerPoint to Keynote, and I couldn't figure out how to get the build to work. But things that go wrong. There was a company last year forgot to renew their domain name. Some of you might know them or even work for them. Think what happens if you forget to renew your domain name. Like companyname.com, right? No email, no Slack, no all your monitoring systems, all your internal systems, everything's down. What was left was their Twitter handle, which did not depend on their domain name, and their CEO apologizing on Twitter while they tried to get the domain back. It was quite entertaining if you weren't a user of that company or worked there. So think about that. The DNS is one of the soft underbellies of all these systems. If anything can go wrong with DNS, you have a serious outage, and it's one of the areas where I think about how do you build a really robust DNS architecture? Do you have multiple suppliers? Do you have multiple DNS names that you can resolve everything to? Do you have an alternate, DNS, primary name that your software will fail over to if for some reason it can't get there on your other name? There's all kinds of things you could actually do if you thought through what might go wrong with DNS. Another one up here, security certificates. They expire, things go down. It's happened to all of you. It's happened to me multiple times. It's happened pretty much everywhere. It's just one of those things. So you have to build something that watches for the dates on security certificates and shouts at you until you actually update them. And then a data center flooded in Hurricane Sandy. I have a friend that was dealing with that for a few months. And something's likely to go wrong with you tomorrow. So, oops. Sorry. Yeah, so that's what I had. I'll be around through lunch. I have to run to the airport this afternoon to get on a plane. I'm worried about the Lyft ride to get there, but I should be fine once I'm on the plane. I store a bunch of my slides at my GitHub account. If you can find me on Twitter at AdrianCO, because you don't have to spell Cockcroft that way. And it's my same ID on GitHub, and there's a whole bunch of stuff there. But these slides are there, and the chaos engineering slides, and a few other interesting slide decks that I've done recently. So that was it. Hopefully that was interesting, and we can all go to lunch. Thanks.
Thank you.